About 20 years ago, when the existence of black holes was just being accepted, a lot of us asked a very simple question. What would it look like if we could take a picture of a black hole?
It's not about what you see, but what you don't see. On Wednesday, scientists unveiled the first direct visual evidence of a black hole.
In April of 2017, all the dishes in the Event Horizon Telescope swiveled, turned, and stared at a galaxy 55 million light years away. And we are delighted to be able to report to you today that we have seen what we thought was unseeable. We have seen and taken a picture of a black hole. Here it is.
I was stunned by how fascinated people were with the black hole. The day after the announcement, the picture was in the front page of every single newspaper anywhere in the world.
I mean, we knew it was a good result, but it was amazing to see how the world reacted to it.
Unlikely as it sounds, we now have an image of that invisible space anomaly, a black hole.
This is amazing. The first picture ever of a black hole.
We now know clearly that black holes drive large-scale structure in the universe. And we now have an entirely new way of studying general relativity in black holes that we never had before. And as with all great discoveries, this is just the beginning.
So, of course, our experiment isn't done. Once that initial excitement died down, we went right back to the drawing board and we said, okay, we have more data in our hands from that observing campaign. We have this other black hole. We've been working very hard at it, and hopefully we'll be able to share the results soon.
But very much along the lines of what is inferred for M87 and Sagittarius A.
A black hole is a warping in space-time that is so strong that not even light can escape from it. And you can go quite close to a black hole, but if you cross that virtual surface that we call the event horizon, then you'll never be able to come out from it.
It's a place in the universe where our ideas of how the smallest things work with quantum mechanics and how the largest things work with gravity and Einstein's theory of general relativity get married to one another, like they both play a role in the event horizon of a black hole.
That has an impact on the images. This is the point.
So when we asked ourselves which are the best black holes to take a picture of, only two of them cross the limit. One of them is the black hole in the center of our galaxy, because it's the closest, and the other is the biggest black hole, and that is the black hole in the center of the M87 galaxy. M87 is so slow that it stays still for us. This is why we started with the M87 galaxy, and we moved later on to the black hole in the center of our own galaxy.
It can be a little bit broader. And if you actually zoom in here...
The Event Horizon Telescope is an international collaboration. Just by virtue of how we conduct this experiment, we need telescopes all across the globe. In fact, what we really did was get telescopes on different continents to work in unison as if they were one telescope. It is centered here at the University of Arizona. We are the PI institution, and we actually held the first meeting of the Event Horizon here in Tucson. We hosted the meeting.
We made possible 3 of the 9 telescopes of the Event Horizon Telescope, 2 of them here in Arizona, one on top of Kitt Peak and one on top of Mount Graham, and the telescope in the South Pole.
When I got a job when I was 15, it wasn't to buy a car, but it was to buy a telescope. You know, I have been interested in this for a long time. Going to a telescope is perhaps a little bit like going to a monastery. You're locked in a space with nothing to do except for your work. The first part of my work in this project is making it possible to do the observations. And currently, I'm responsible for making the 2 observatories in Arizona and the one at the South Pole work each year. Things we have to worry about that are a little bit surprising are things like the temperature of the cables that carry our signals and how they change during our observation, or the little quartz crystals that do the oscillations that we use to reference our measurements to. You've always got to be checking something. It's like if you're driving and you had, 50 mirrors that you had to be checking all the time. It's a lot of little things, but if you get any of them wrong, then it doesn't work. The SMT is a little unusual because when the telescope turns, the building rotates with it. It's gradual enough that you generally don't notice it unless you can see out a window. A neat thing about being at the telescopes is that there's no better place to just sit and look at the stars the way I did when I was a kid. If you were to ask someone, imagine the strangest thing that must exist in the universe, there's no way they would imagine that there's a point in space where all the laws break down. And so determining whether that's a real thing in the universe and proving it, that seems really cool. So I'm really happy to have the chance to be a part of that.
Einstein told us how to interpret the world in a way that is very counterintuitive. The equations of Einstein's theory are very complex, and the only way to make any progress is to throw them on big supermassive computers and calculate what they predict. So what we do is we make a virtual black hole. We calculate the motion of the plasma and the motion of light coming out of it, and then we simulate the observations just like the real observations happen. We actually have a little machine that we control our simulations with our hands while the simulation is running in real time. And now we're at a point where our tools here at the University of Arizona are so efficient that we can actually render a single simulated image in a fraction of a second. We have spent the last year and a half finessing our tools, given what we know from the previous image, and we are very, very eager to see what this second black hole picture will look like. Is it the same? Is it different? Does it agree with Einstein's theory? Does it not?
University of Arizona have just announced new information about the center of our galaxy.
Literally just announced what they're calling a very groundbreaking discovery and very cool stuff here, Nicole.
Good morning, everyone, and thank you for being here while we share with you our exciting new results about our galaxy, the Milky Way. At its heart, towards the constellation Sagittarius, is Sagittarius A star, the supermassive black hole suspected to reside there. Today, the Event Horizon Telescope is delighted to share with you the first direct image of the gentle giant in the center of our galaxy, Sagittarius A star.
There is a reason why we say seeing is believing. When you see something that you've heard so much about, it suddenly becomes real. And the black hole that we took a picture of is not imagination anymore. It's something as real as our own Earth.
The thing that has drawn me to black holes is this test of theories of physics, theories of the universe. And I really hope that my career and all the things that I worked on and contributed to actually ends up, furthering that.
The release of Sag A star brings us to the end of that top-level goal. But the amazing thing is that the data we've taken since the very first experiment has gotten so much better that astrophysically, we're going to learn a lot more from everything we do after than we do from just these two first pictures.
As humankind, I think we do a lot of things because we're intrinsically curious. We have a sense of wonder about the things around us. The story of the black hole just is a chapter in that book.